morning, dear students. Myself, Dr. Priya, working as Associate Professor in Chemistry, Department of Humanities and Sciences, MLR Institute of Technology. In today's presentation, we are going to learn about examples of thermoresponsive polymers. These are a category of smart materials which are able to respond basing on temperature supply, and a few examples we are going to learn in this session. Polyacrylamide and polyvinyl amide, two examples. So let us start with polyacrylamide. So this is an example for thermoresponsive polymer. So what do you mean by thermoresponsive polymer? Means whenever that polymer material is subjected to some amount of heating, that is, if you supply some amount of temperature to that kind of polymer, so it is able to respond in its change, to bring a change in its properties. So such kind of polymers are called thermoresponsive polymers. So let us go with its examples. First one, it is polyacrylamide. The most commonly studied and first reported thermoresponsive polymer in aqueous solution, that means solvent, it is water. Aqueous solution means the solutions in which water it is used as a solvent, is poly-N-isopropyl acrylamide. Its short form, it is PNIPAM, PNIPAM, or simply we will call it as PNIPAM or poly-N-isopropyl acrylamide. The most commonly studied and first reported thermoresponsive polymer, so which is considered in its aqueous solution. That polymer, it is to be considered in aqueous solution, it is PNIPAM. So PNIPAM is considered to be the gold standard of thermoresponsive polymer. It is a kind of a reference material for all types of thermoresponsive polymers. We can consider that one as a standard one or gold standard one, or we can call it as a reference for thermoresponsive polymers. So it is having major applications in biomedical form. Biomedical applications it is having a lot, especially in the case of biomedical applications. This is fixed like a standard thermoresponsive polymer. So let us see how it is prepared. So it is prepared by free radical polymerization of N-isopropyl acrylamide. N-isopropyl acrylamide, it is monomer. So this monomer, if it is subjected to addition polymerization reaction through free radical mechanism. Free radical means formation of a free radical should take place with the help of an initiator, that is radical initiator. So that means homolytic dissociation of bond should take place between the two atoms. If homolytic dissociation takes place, each atom will acquire electron. Bond is nothing but equal to 2 electrons. So if homolytic dissociation takes place, then as a result of that one, each atom will acquire a electron. So it is represented by a dot, that is called free radical. So for this free radicals to produce, we have to make use of one initiator. So that is azo-bis isobutyronitrile. So this is playing the role of radical initiator. That the first unit of monomer, that is N-isopropyl acrylamide, if it is treated with azo-bis isobutyronitrile, which is acting like an initiator, it is able to form corresponding free radicals for this monomer, that is N-isopropyl acrylamide. Then it is involving in propagation reaction with the free radical mechanism, and then chain termination will take place. As a result of this, poly-N-isopropyl acrylamide formation will take place. So as I told you, it is example for amide, polyamide. Polyamide. What is amide functional group? C double bond O NH. This is the functional group of amide, and here if you notice, this is C double bond O and then NH. This is what we call as amide functional group, and this entire group it is going to repeat n number of times. That's why it is an example for polyamide. So this is the structure of poly-N-isopropyl acrylamide. So how it is prepared? So it is prepared by subjecting N-isopropyl acrylamide to addition polymerization reaction through free radical mechanism with the help of azo-bis isobutyronitrile as an initiator. Then it is able to produce its corresponding polymer compound, that is called polyacrylamide, or we will call it as PNIPAM or poly-N-isopropyl acrylamide. So what are its major applications? As I told you, it is having in biomedical field, it is having lot of applications. First one, it is drug delivery. It is used in temperature responsive drug delivery systems for controlled release. And then even in biosensors also it is having lot of applications. And these were employed in temperature sensitive biosensors for which are able to identify or detect biological changes in the surroundings. And we can use this polyacrylamide as a smart coating applied in responsive coatings for surfaces that are able to change the properties with respect to change in the temperature basing on the climate changes, or we can say weather conditions. This coating, it is very much helpful to give a response on the surface of the material with respect to its physical properties. And then in water purification also it is having lot of applications. It is used in a temperature controlled separation process like membranes, that is what we call as filtration. In water purification we have to make use of membranes. If those are made up of this kind of polyacrylamide material, then basing on the temperature it is able to separate that salts that were produced in the water sample. So that's why it is named like temperature controlled separation process. Using this polyacrylamide it is possible. So, and coming to the next one, that is polyvinylamide. Polyvinylamide, this is a class of thermoresponsive polymer, as I told you, which is considered to be the second most explored polymer. So first one it is polyacrylamide, and the second developed one it is polyvinylamide. Polyvinylamide is also an example for thermoresponsive polymer. Poly-N-vinyl caprolactam, that is PVCl, is the best example for this category, that is polyvinylamide. Example for polyvinylamide, it is poly-N-vinyl caprolactam. So this is the structure of N-vinyl caprolactam, that is poly-N-vinyl caprolactam. So this is also an example for amide functional group. So if you notice, this is C double bond O. Here it is having carbon, C double bond O, and then N. That H it is replaced with vinyl group, right? So that's why it is mentioned like N-vinyl. On N means nitrogen, it is having a substitution of vinyl group. So where is this N it is present? It is present in the place of carbon in caprolactam. So this is what we call as caprolactam. 8-membered ring will be there. In that 8 carbons, 1 carbon it is replaced with nitrogen, and this nitrogen it is having a substitution of vinyl group. So that's why it is named as N-vinyl caprolactam. That is its monomer. On subjecting this one to polymerization reaction, it will convert into poly-N-vinyl caprolactam. So that's why it is the best example for polyvinylamide. And it is having some advantages as well as disadvantages. Let us see one by one. Its LCST, it is very low, or we can say its LCST of this polymer lies in between the body and the room temperature, that is 31 degrees centigrade. So it is very low. And then this LCST does not depend upon the chain length or environment such as pH. So if pH varies, it doesn't affect the LCST value. And then if polymer chain length is more or less, it doesn't bother. So that's why it will possess a very less CST, that is fixed. So that is one of the most important advantages for or properties of polyvinylamide. And coming to the next one, that is LCST does not depend, this one it is discussed. And coming to the disadvantages part, disadvantages will include this polyvinylamide is having a low glass transition temperature. That means whenever the temperature is very low, like minus 60 degrees centigrade is very low, then it possesses a very low glass transition temperature, that is around minus 60 degrees centigrade, and then low melting temperature, that is around 60 degrees centigrade. So because of which it is able to cause mechanical strength, it is very less, or it is able to lack this mechanical strength. So it is lack of this mechanical strength because of these two. Its glass transition temperature it is very low, and then melting point is also, or melting temperature it is also very low, and it is poorly biodegradable in nature. That means very slowly it is involving in decomposition, very rarely and very poorly. It is degradable in nature, but a slow process it is. Decomposition will take place very slowly. So that is the one more disadvantage. Coming to the applicative part, as I told you, it is an example for smart material, and moreover stimuli responsive applications it will have, like thermo or pH sensitive hydrogels. Basing on pH variation or temperature variation, accordingly it is able to change its physical properties. That's why it is an example for smart material. And then in energy storage also, it is having a lot of application, energy storage devices as binders or components in batteries or supercapacitors like that. Such kind of energy storage devices also, it is having lot of applications like binders or components in the case of batteries or supercapacitors. And then sustainable packaging, even in packaging also it is having lot of applications, biodegradable alternatives to conventional plastics. So better to prefer this polyvinylamide as a biodegradable alternate for normal existing conventional or we can say traditional plastics. So in today's session we have discussed about examples for thermoresponsive polymers. In syllabus we have two. One is polyvinyl amide, another one it is polyacrylamide, that is pinipam. So two examples we have discussed. So that's all for today's class. In the coming session we are going to learn about a few more smart materials, a few examples or few categories of smart materials. So that's all for today's class. Have a nice day. Thank you.